Hello and welcome back to the channel. In today's video, we're overclocking the AMD Ryzen 5 8600G APU all the way up to 5250 MHz using the GIGABYTE B650E Elite AXI's motherboard and custom loop water cooling. This will be the second Hawk Point APU I overclock on this channel. I previously overclocked the Ryzen 7 8700G, and it was quite interesting to kind of see everything that I learned while overclocking the 8700G also be confirmed with the 8600G. Just like with the 8700G, in this video I'm focused specifically on overclocking the CPU cores, and I will address integrated graphics overclocking in the next SkatterBencher guide. Alright, let's jump into the overclocking. The Ryzen 5 8600G is the second of two APUs in AMD's Zen 4 Ryzen 8000 APU lineup featuring the Phoenix 1 die. Hawk Point is the successor to the Ryzen 5000 Cezanne APUs launched in 2021. The Ryzen 8000 series APUs come to market in two distinct configurations. The Ryzen 7 8700G and the Ryzen 5 8600G feature the Phoenix 1 die with Zen 4 cores, and the Ryzen 5 8500G and the Ryzen 3 8300G feature the Phoenix 2 die with a mix of Zen 4 and Zen 4C cores. A lot has been said about the difference between Zen 4 and Zen 4C cores. I won't regurgitate everything here, but the point is that the core architecture is identical, while Zen 4C cores have a smaller footprint. The benefit is that you get more compute per area, but the trade-off is that you also have higher hotspot temperatures and lower frequencies. The Ryzen 5 8600G has 6 Zen 4 cores with 12 threads. The base frequency is 4.3 GHz and the listed maximum boost frequency is 5 GHz. The TDP is 65 watt and the TJ max is 95 degrees Celsius. In this video, we will cover 3 different overclocking strategies. However, before we jump into the overclocking, let's first have a look at the hardware and the benchmarks that we'll be using in this guide. The system we're overclocking today consists of the following hardware. In March 2023, I launched the EFC-SB SkatterBencher edition in collaboration with Elmo Labs. The EFC-SB is essentially a variant of Elmo Labs EasyFan controller, but with a couple of additional features and the SkatterBencher color scheme. I explain how I use the EFC devices in many previous SkatterBencher guides. I monitor the ambient temperature, water temperature, and fan duty cycle, and I include those measurements in my stability test results. I also use the device to map the radiator fan curve to the water temperature. Without going into too many details, I've attached an external temperature sensor from the water in the loop to the EFC, and then I use a low-high setting to map the fan curve from 25 to 40 degrees water temperature. The main takeaway from this configuration is that it gives us a good indicator of whether the cooling solution is saturated. We use Windows 11 and the following benchmark applications to measure performance and ensure system stability. Before we start overclocking, we must check the performance at default settings. The default precision boost 2 parameters for the Ryzen 5 8600G are as follows. Here's the benchmark performance at stock. Here are the 3DMark CPU profile scores at stock. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 4512 MHz with 1.225 volts. The average CPU temperature is 78.5 degrees Celsius. The average CPU package power is 87.8 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 4699 MHz with 1.285 volts. The average CPU temperature is 79.6 degrees Celsius. The average CPU package power is 87.8 watts. The boost frequency at one active thread is about 5045 MHz and gradually trails off to 4803 MHz when all cores are active. All but one of the 6 cores surpassed the listed maximum boost frequency of 5 GHz. However, none achieved the programmed Fmax of 5050 MHz. Of course, we can increase the power limits by using Precision Boost Overdrive 2, and that's exactly what we'll do in our first overclocking strategy. However, before we do that, make sure to locate the clear CMOS header. Shorting the clear CMOS header will reset all of your BIOS settings to default, which is helpful if you want to start your BIOS configuration from scratch. In our first overclocking strategy, we simply take advantage of enabling Precision Boost Overdrive and enabling AMD EXPO. With the launch of Zen 3, AMD introduced an improved version of the Precision Boost Overdrive Overclockers toolkit. They called this Precision Boost Overdrive 2, and this toolkit allows you to manually adjust some of the parameters that affect the Precision Boost boosting algorithm. Precision Boost Overdrive 2 builds on the PBO implementation of Zen 2. In addition to the overclocking knobs from Zen Plus, PPT, TDC and EDC, and Zen 2, Boost Override and Scalar, Precision Boost Overdrive 2 also introduced Curve Optimizer. There are essentially 3 levels of Precision Boost Overdrive. In this overclocking strategy, we're simply enabling Precision Boost Overdrive, whereas in the following strategies, we'll explore tuning the parameters. By enabling Precision Boost Overdrive, we rely on the motherboard pre-programmed PBO parameters. We find that the following values have changed. Increasing the PPT and to a lesser extent the TDC and EDC will help unleash the frequency in multi-threaded workloads previously limited by either of these parameters. EXPO stands for AMD Extended Profiles for Overclocking, and it's essentially an AMD technology that allows for ubiquitous memory overclocking on systems, AMD systems, that support DDR5 memory. EXPO allows memory vendors such as G.Skill to program higher performance settings onto the memory sticks. If the motherboard supports EXPO, you can enable higher performance with a single BIOS setting. So it saves you from a lot of manual configuration. Upon entering the BIOS, in easy mode, set XMP EXPO profile to EXPO 1. Switch to advanced mode. Enter the advanced CPU settings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to enabled, then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. We get a decent performance uplift in the heavier multi-threaded benchmark applications by enabling Precision Boost Overdrive. However, in most benchmarks, the performance uplift is minor to non-existent. The geomean performance improvement is plus 0.81%, and we get a maximum improvement of plus 6.85% in Geekbench 6 Multi. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 4686 MHz with 1.296 volts. The average CPU temperature is 95.4 degrees Celsius. The average CPU package power is 107.7 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 4772 MHz with 1.334 volts. The average CPU temperature is 88.7 degrees Celsius. The average CPU package power is 101.7 watts. In our second overclocking strategy, we fine-tune the Precision Boost boosting algorithm using the PBO2 toolkit. In addition, we also optimize the memory subsystem performance. Fused maximum frequency, or Fmax, is one of the infrastructure limiters governing the Precision Boost boosting algorithm. Essentially, Fmax determines what is the maximum frequency each of your cores inside your CPU can run at. Boost Clock Override, or Fmax Override, is one of the overclocker tools available in the PBO2 toolkit. It allows the user to override the arbitrary clock frequency limit between minus 1000 MHz and plus 200 MHz in steps of 25 MHz. It is important to note that the Fmax Boost Override only increases the upper limit of the frequency ceiling. it doesn't act as a frequency offset. So at the end of the day, the precision boost algorithm will still determine the effective frequency of your CPU. When we increase the if-max boost limit by 200 MHz, the new if-max is 5250 MHz. Curve Optimizer is a very important new tool in the Precision Boost Overdrive to Overclockers toolkit. Essentially, Curve Optimizer allows end users like you and I to adjust the CPU voltage frequency temperature curve, or VFT curve. The VFT curve determines what voltage should be used for a given frequency and a given temperature. As the frequency increases and as the temperature increases, you'll need more voltage. Curve Optimizer adjusts the VFT curve by offsetting the voltages of the factory fused VFT curve. By setting a positive offset, you increase the voltage point. Conversely, you decrease the voltage point by setting a negative offset. The traditional approach for overclocking AMD Ryzen APUs and CPUs is to use a negative curve optimizer. Two things happen when you do that. First, we effectively undervolt the CPU and tell it needs less voltage for a given frequency. And as a consequence, at a given voltage, it can apply a higher frequency. Second, the CPU temperature will be lower because you use less voltage at a given frequency. That extra thermal headroom will also encourage the Precision Boost algorithm to target higher voltages and frequencies. Like in the past, per-core curve optimization can be really beneficial, as some cores can curve optimize much more than the others, and therefore you can extract more frequency on some cores than on the other cores. The manual curve optimization process can become quite convoluted because you're effectively optimizing your CPU for a very wide range of scenarios, going from light, single-threaded workloads to heavy all-core workloads. I usually spend quite a bit of time curve optimizing my CPU. For this guide, I wanted to rely exclusively on the tools available in the OCCT stress test application. Here's my broad approach. I start off with a negative curve optimizer of -15 for each core. Then I use the OCCT CPU stability test with small dataset, extreme mode and steady load type. I core cycle through each core for 60 seconds and 2 operating threads. Then I increase the negative curve optimizer magnitude by 5 steps for those cores that didn't crash, and I reduce that negative curve optimizer magnitude by 5 steps for the cores that did crash. Once all the cores are dialed in, I run another OCCT AVX2 and SSE stability test, intending that to pass for 30 minutes without any of the cores failing or clock stretching. Again, when a core fails, I reduce the negative curve optimizer magnitude by 5 steps. And once all that is done, I run through the usual benchmark suite and stability tests used in this guide. And if there are no instabilities, I consider my curve optimizer settings as stable. On Hawk Point APUs, the memory subsystem comprises of 3 important parts: the Infinity Fabric, the Unified Memory Controller, and the System Memory. These parts are also referred to as the F-clock, the U-clock, and the M-clock. Now, old school Ryzen overclockers or first generation Ryzen overclockers know that these parts are intimately connected, and they used to be very connected. You wouldn't be able to tune one without affecting the other. However, on modern Ryzen CPUs, we can tune each of these parts independently. When it comes to optimizing the memory performance subsystem, there were 2 things that I wanted to address in particular. First, I wanted to fix the downclocking of the F-clock and the U-clock. And second, I wanted to make sure the U-clock and the M-clock run in sync. To solve the first problem, we simply enable the SoC Uncore OC mode in the AMD overclocking submenu. This disables all power-saving technologies affecting the clock frequencies of the memory subsystem. To address the second target, we simply set uClock div1 mode to uClock equals memclock. The memory controller frequency is tied directly to the system memory frequency. I can run either at the same or half its frequency. You usually prefer to run the memory controller and system memory at the same frequency for performance reasons. However, if your memory can run very high frequencies, then it's possible running the memory controller at half the frequency still provides better performance. We run the memory controller frequency in sync with the system memory for this OC strategy. At DDR5 6400, the memory controller frequency is then 3.2 GHz. Do note that this wasn't immediately stable. I also had to increase the SoC voltage to 1.3 volt to make sure that the memory controller could run at the same frequency as the system memory. A last quick setting I wanted to discuss before moving on to the BIOS settings is the high bandwidth memory option. I used this in previous guides and they seem to provide additional performance benefits, but GIGABYTE is pretty tight-lipped on what it does exactly. Enabling the settings may cause instability, so it's up to you to see if your memory is stable when enabled. Upon entering the BIOS, in easy mode, set XMP EXPO profile to EXPO 1. Enable XMP EXPO high bandwidth support. Switch to advanced mode. Go to the settings menu. Enter the AMD overclocking submenu. Click accept. Enter the DDR and Infinity Fabric frequency timings submenu. Enter the Infinity Fabric frequency and dividers submenu. Set uClock div1 mode to uClock equals memclock. Leave the Infinity Fabric frequency and dividers submenu. Leave the DDR and Infinity Fabric frequency timings submenu. Enter the Precision Boost Overdrive submenu. Set Precision Boost Overdrive to advanced. Set PBO limits to motherboard. Set CPU Boost Clock Override to enabled positive. Set Max CPU Boost Clock Override to 200. Enter the Curve Optimizer submenu. Set Curve Optimizer to per core. For every core, set Curve Optimizer sign to negative. Set Core 0 and Core 4 Curve Optimizer magnitude to 40. Set Core 1, 3 and 5 Curve Optimizer magnitude to 45. Set Core 2 Curve Optimizer magnitude to 35. Leave the Curve Optimizer submenu. Leave the Precision Boost Overdrive submenu. Enter the SoC and Core OC mode submenu. Set SoC and Core OC mode to enabled. Leave the SoC and Core OC mode submenu. Enter the SoC voltage submenu. Set SoC voltage to 1300. Then save and exit the BIOS. We reran the benchmarks and checked the performance increase compared to the default operation. After the impressive Curve Optimizer Undervolt and a maximum Fmax increase, we find that the performance improvement is pretty substantial across the board. Both single-threaded and multi-threaded benchmark applications improve noticeably. The geomean performance improvement is plus 7.52%, and we get a maximum improvement of plus 16.07% in Geekbench 6 Multi. When running the OCCT CPU AVX2 stability test, the average CPU core effective clock is 4978 MHz with 1.273 volts. The average CPU temperature is 93.7 degrees Celsius. The average CPU package power is 116.9 watts. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 5040 MHz with 1.322 volts. The average CPU temperature is 92.1 degrees Celsius. The average CPU package power is 108.7 watts. The boost frequency at one active thread is about 5173 MHz and gradually trails off to 5039 MHz when all cores are active. 2 of the 6 cores surpass 5.2 GHz and every core can boost to over 5.1 GHz in single-threaded workloads. In the third and final overclocking strategy, I'm pursuing a manual overclock. Now, originally, I wanted to do exactly as I've done in previous AMD overclocking guides, and that is using the OCCT AVX2 all-core workload as my reference workload. But turns out that there's pretty much zero overclocking headroom in this particular workload. The Precision Boost algorithm already maxes out the all-core AVX2 frequency, essentially. So then I decided to just forego the AVX2 stability requirement and try to squeeze more frequency for OCCT SSE all-core workload. And then also, of course, in the hope that it would pass all of my benchmarks. Anyway, before we get into the BIOS settings, let's first have a look at the AMD Hawk Point clocking and voltage topologies. The standard Hawk Point platform has a 48 MHz crystal input to the integrated CG-PLL clock generator. The CG-PLL then generates a 48 MHz clock for the USB PLL and a 100 MHz reference clock for the FCH, which contains the CCLK PLL for the CPU cores and several SoC PLLs. The CCLK PLL 100 MHz reference clock drives the 200 MHz VCO, which is then multiplied by an FID and divided by a DID. Each CCX has its own PLL, with the cores within that CCX running at the same frequency. The SoC PLLs include a wide range of PLLs. However, the SoC PLLs are not relevant for manual CPU core overclocking. AMD Hawk Point's voltage topology is similar to that of previous Ryzen processors. There are 4 primary power supplies from the motherboard VRM to the processor. The VDDCR voltage rail provides the external power for 3 internal voltage regulators. VDDCR CPU provides the voltage for the CPU cores within the CCX. The voltage rail can work in either regular or bypass mode, but it is always in bypass mode on Hawk Point. That means the voltage of the cores is always equal to the VDDCR external voltage. The end user can change that voltage in the BIOS. The VDDCR SoC voltage rail provides the external power for multiple internal voltage regulators on SoC for the various IP blocks, including but not limited to the memory controller, the SMU, PSP, and so on. On many core processors like the Ryzen Threadripper, per CCX fine-tuning can become quite a lengthy task because there's so many different CCXs to fine-tune. But on this 8600G, we have exactly one CCX, which contains all of the 6 Zen 4 cores. So it makes the per CCX tuning or the manual overclocking a lot simpler and a lot faster. Our limiting factor will ultimately be the cooling solution, as power consumption increases exponentially with operating voltage and temperature scales somewhat linearly with power consumption. The maximum voltage will be determined by the application we're tuning for. So the first step in our tuning process would be to set a fixed CPU ratio and check the maximum temperature when running our workload. If there's thermal headroom left, increase the operating voltage. Once we know the maximum voltage, we can tune the CCX. Simply increase the ratio until the application shows signs of instability, then back off. No more, no less. In our case, we reach near TJ max temperatures with a voltage of around 1.35 volt. That gives us sufficient headroom to push the CPU core clock frequency to 5.1 GHz. Now that we know the ins and outs of a Ryzen 5 8600G APU manual overclocking, let's jump into the BIOS. Upon entering the BIOS, in Easy Mode, set XMP EXPO profile to EXPO 1. Enable XMP EXPO high bandwidth support. Switch to Advanced Mode. In the Tweaker menu, set CPU ratio mode to all cores. Set CPU clock ratio to 51. Set uClock div1 mode to uClock equals memclock. Set CPU vCore to 1.3 volt. Then save and exit the BIOS. We rerun the benchmarks and check the performance increase compared to the default operation. It's highly unusual for a manual overclock to outperform the stock configuration in single-threaded benchmarks, because by enabling OC mode, you forgo the high precision boosting frequencies in single-threaded workloads. However, in this case, our manual overclock of 5.1 GHz is higher than the stock maximum frequency of 5.05 GHz. So we see a performance uplift in all benchmarks, which is pretty neat. The geomean performance improvement is plus 5.41%, and we get a maximum improvement of plus 14.84% in Geekbench 6 Multi. When running the OCCT CPU AVX2 stability test, Unfortunately, the processor is not stable. When running the OCCT CPU SSE stability test, the average CPU core effective clock is 5100 MHz with 1.352 volts. The average CPU temperature is 90.5 degrees Celsius. The average CPU package power is 105.5 watts. Since we use a fixed clock frequency of 5.1 GHz, each core operates at that frequency, whether that's in a single core workload or an all-core workload. Due to the stock frequency limit of 5050 MHz, the frequency of a manual overclock is at all times higher than stock. Alright, let's wrap this up. Overclocking the Ryzen 5 8600G was pretty interesting to me, but I'm not sure if it was that interesting to you. Essentially, the story is the same as we had with the Ryzen 7 8700G. That is, the AMD Hawk Point CPU cores have very limited overclocking headroom. Now, whether that's due to the specific Phoenix architecture or if it's due to the TSMC N4 process nodes, we don't really know that. The only thing that we can really know is that achieving only 5.1 GHz for a modern CPU is a little bit disappointing. That said, it's actually quite easy and quite fast to find more performance in the Ryzen 5 8600G. You simply enable EXPO, you adjust a couple of parameters with your Precision Boost Overdrive, you do a little bit of curve optimization and add this fmax boost override, and voila, you can get a little bit more extra performance. We saw up to plus 16% in some benchmarks, so that's not too shabby. Anyway, that's it for me for this video. In a couple of SkatterBencher guides, I will also try one of the Phoenix 2 Hawk Point APUs, so if you're interested in that, stay tuned, maybe subscribe. I want to thank you for watching, and of course, I want to thank the Patrons for their continued support. I'll also have a written version of this video up on my blog if you want to read through the BIOS settings or check some of my benchmark results. And that's it. See you next time.